Yes. So how did we build this wonderful Serval mesh software that we've got today? Okay, this is a diagram of the system architecture of Serval mesh running on an Android system. As I explained earlier today, we've got Linux kernel, and everything uses Linux kernel via the Android system libraries. We have this component, which is basically the common component in everything that we're building. All of our core Serval functionality, all of the core code is in this thing which we call Serval D, which is the daemon. That's approximately, where's my notes? No, I've got some notes here. Okay. That's got about 23,000 lines of C code and about 2,500 lines of C header code in it. At the beginning of this year, or around the time that the KiwiX was going on, instead of this architecture, it was radically different. This was much, much smaller. The Java Android application, which we call Batphone, was much bigger, and we had two other separate applications, WebSMS, SMS Droid, which actually did a lot of the work of sending SMSs, and we also had Asterisk in there doing the telephone, all the telephony and so forth. So it was quite a mess. As Paul said, the APK to download was about 5 megabytes or something like that. Now it's gone down to just under 2, and it unpacks to not that much bigger. If you look across the top there, you can basically see the functions on the home menu of Serval. If you start up the Serval program, you've got the main screen with buttons for all the different functions. Well, those are the top things across there. You've got the settings button, the peer list button. So if you press peer list, what happens is that the Java code, whoops. Yes, I hope so. The Java code invokes the C code through what's called the JNI interface, which is the way that Java code can be set up so that it can invoke C code. You can embed C code into Java. It does it through an interface which actually resembles the normal Unix command line interface. So it assembles a set of strings, puts them in a list and says, here, run as though I had just invoked you like a command line. This comes in useful later when it comes to testing. It invokes a function which is what we call part of DNA, which is distributed number architecture, which is one of the early innovations of Serval, which is a way to map a telephone number to a device. Because if you think about when you make a phone call on a mobile telephone, it contacts the cell tower, goes to Telstra's central registry, who happens to know, well, where if I'm calling my brother, well, your brother is in cell number 500 over in the middle of Sydney. So it knows to route the call there, send out the signal there, and so forth. So there's a big central telephone directory that the telcos maintain. With Serval, there is none of that. There is no central telephone directory. What happens when you phone a number? How does it know which phone to ring? How does it know if the phone is actually in range? What we have is a protocol we've designed called DNA resolution. What that does is it broadcasts a packet to everything that can receive the packet, saying, anyone who knows this number, please reply. And all the telephones that know about that number, or that even are that number, send back a reply. And it accumulates the replies and presents a menu of all of the options, if there was more than one, to the user and says, well, here's the replies I've got, which one is it? So every telephone needs to know what its own number is. When you start the Serval software, you have to choose the telephone number that you want to use. And you can also optionally put in a name to help people distinguish between you with that number and someone else with the same number. So it depends a lot on trust. The idea is that in a post-disaster situation or out in the field with KiwiX or whatever, everyone's chosen their own number and you just trust that people are not trying to hijack other people's number. I was saying, oh, I'll put in his number, and so when they're calling him, they're really going to be calling me, and I'll put on a funny voice and they'll think they're talking to him. Right? But it could happen. So there's a lot of trust involved, that people are only going to choose the numbers that should be there. Anyway, DNA is the protocol that we've invented that does that. What does it resolve to? So I put in a telephone number, searched by that, and I get back what? What I get back is what we call the Serval identifier. Every instance of Serval which is running on a telephone, the first time it starts, rolls a random cryptographic identity, which is actually a public key in a private-public key pair. That number, from that point forth, uniquely identifies your telephone. So you can change your number and your name on your telephone from that point on, but the SID remains the same, at least until you completely erase the Serval software from your telephone. The next time you install it, you will get a different SID. So how can an SID be used to contact all of the other telephones? Well, that's this lane, the Mesh Datagram Protocol. The Mesh Datagram Protocol is a little bit analogous to the UDP protocol in the internet. UDP stands for Unreliable Datagram Protocol. The idea, the way that the internet works is you can think of it as a delivery postal service where you can throw datagrams, which are basically just a packet of data from any length up to a maximum. You throw them into the internet with a destination address and a source address, which is your source address. The internet guarantees that if it gets to the destination, it's intact. Otherwise, it just doesn't get there. You don't receive corrupted datagrams. If a datagram gets there, it is intact. But it reserves the right to just drop them on the ground and not deliver them. That's what the datagram protocol is. So we've got a similar protocol. What we realised early on in Serval is we can't depend on the internet protocol to do our work for us, because we may well end up implementing this without anything resembling the internet there. We may have custom radio modules on here that talk to each other directly. So we needed our own protocol layer that we could layer on top of the internet. We invented it, and it's called Mesh Datagram Protocol. In internet land, an address, an IPv4 address, is that dotted quad that everyone's familiar with. It's 32 bits of information. In MDP land, an address is not structured like that. It's, how many bits is it? 256 bits of public key, which is a random number. The chances of two people rolling the same one are infinitesimally small. And there's a huge number of potentials out there.
If your random source is strong.
Yes, that's the one, exactly. So basically, if you know someone's address, you already have the information you need within the crypto system to send them messages that only they can decode. You also have enough information if you exchange your SID, or that is to say network address, with another phone. Both the phones now have all the information they need to negotiate a secure session in the same way that your browser negotiates a secure session when you're using HTTPS to do online shopping or something. So by using the public key as the network address, the fundamental innovation of Mesh Diagram Protocol is that you don't need to do any more steps to get secure networking. The Mesh Datagram Protocol, a packet basically looks like this. We invented our own packet. And one of the important things about the packet is we realised we have to squeeze down the byte count as much as possible. TCP and UDP on top of TCP, and then other applications within that are quite wasteful, because you get this kind of perfect encapsulation as you go down the layers of the network model. And the perfect encapsulation is that you get given, one layer gets given a packet to transmit. It doesn't know anything about the contents of the packet. It just puts its own extra bytes at the beginning and the end as an envelope and passes it down to the next layer. So as you get down your layers to the final physical transmission, you end up with massive amounts of envelopes accreted around the thing, and your minimum packet size can easily be 30 or 100 bytes. The minimum packet size for us is 4 bytes. Doesn't say much, but you can get it down to 4 bytes. The first byte is basically a bunch of flags telling you more about what's present after that. Then the sender SID and the recipient SID, these are analogous to the source and the destination addresses on an internet packet. Those can be between 0 and 33 bytes. If you have, because our addresses are so hugely long, 32 bytes, you don't want to put them in every single packet, so we use abbreviations. So once a system has seen a full SID, it remembers it, and whenever it sees a prefix which only matches that SID, it says, well, that must be that one. So we use a system of abbreviations to be able to pull the byte count down. Then the routing layer, which is the one that actually does all the multi-hop, so if I'm sending a packet from this phone to that phone, it has to travel through 3 in between to get there. The routing in each level inserts the RX SID field there, based on which one it wants to send it to next. The broadcast ID is used if it's a broadcast packet. There is no recipient SID. It's going to everyone. So instead what it does is it rolls a sequence number so that the routing software is able to disambiguate and not repeat sending the same packet more than, it doesn't send the same packet on more than once. Then we have a time to live field, which is basically 5 bits. So, which is used to make, that's the classic network way of avoiding infinite loops, where a packet goes round and round and round and round. Every time a packet gets passed on, the time to live field is decremented by 1. When it's 0, it never gets sent any further. That's the standard way. QoS are 3 bits that tell the routing software basically what sort of priority this packet has. Voice packets, for example, that are used for a voice call have a higher priority. Packets that are being used to send or reply to DNA lookups have a lower priority. Packets being used to transfer files for Rhizome have a much lower priority than that. That's to ensure that you get, basically voice calls don't get clogged up when there's lots of big Rhizome transfers happening at the same time. Then the rest of the packet looks different depending on the settings of the E and the S bits, the encryption and the signed bits up the top, of which there are 3 possible combinations. The normal one is a normal clear packet. This is the way the internet works, where you basically have a source port, a destination port. TCP/IP port numbers are 16 bits each. Ours are 32 bits each, so we've got a lot more ports that we can use, but we encode them in a UTF-8 kind of way, so that if you've got the lower port numbers, you don't need to use the full 4 bytes to represent them, and again, more byte squeezing. And then the clear content, which is the number of bytes, which is up to 65,000. If it's signed but not encrypted, it's exactly the same, but a signature, a cryptographic signature, 64 bytes, gets appended onto the end. That basically prevents any forgery. That signature is signed using the private key that corresponds to the recipient's public key, which is part of the top there. So you can use that to verify that it actually came from that recipient. If someone's trying to forge content saying, oh, I'm that recipient, oh, and here's the content, you can check the signature and say, well, no, that didn't come from you because it's not signed by your private key.
Checking as the sender.
Yes, as the sender. Sorry, the sender. It's signed by the sender one. If it's encrypted and signed, it goes through the crypto box, which is the elliptic curve cryptography encryption, which encrypts and signs in the same operation. And then the port numbers and the content are no longer visible except to the recipient. Sorry?
Thank you.
Does he have a name? Okay.
No, he doesn't have it.
Okay. So, at the moment, our MDP is only carried over internet. So what we've done is we've layered it on top of UDP, on top of IP. At the moment, in the future, we'll be doing it a different way. The way we do that is that we fill up a UDP packet with as many of those MDP packets as possible in what we call an MDP overlay frame, which basically contains a bunch of stuff at the beginning and then just a whole bunch of concatenated packets. And the way we work is if we're sending an MDP packet, on Wi-Fi it's as cheap to send a short packet as it is to send a long packet, basically. So if we've got a short packet to send, we stuff as many other long packets of other stuff as we possibly can. So the Rhizome system, for example, always keeps a list of packets that it wants to send. It just fills up a pool with them and says, send these when you can. Also, the routing logic also is probably going to be able to do the same. It's going to say, well, it'll be nice to transmit these out if you can, if you've got space. If you haven't, don't worry about it. And there's even a priority between those. So if you've got one packet that you absolutely must send, which is the next 10 milliseconds of a voice call, and that's all you've got to send, well, at the same time, you just piggyback a whole bunch of Rhizome content on it, a whole bunch of routing information content, and out it goes. Big.
Couple of minutes.
How many?
Just a
couple of minutes, okay. The Serval D component that we've built features in the OpenBTS system, which is the commotion wireless system, which is not an Android system at all. What we have is we have Asterisk and we have Serval D, and there's a way, and we've invented APIs for the Asterisk to use Serval D to resolve numbers, so that when someone calls in, it will actually send out a DNA request, resolve it, say back to Asterisk, say yes, you can call that one. When someone's calling out, it'll actually use Asterisk to resolve the call. So it integrates with Asterisk. We also test our software quite extensively. All the functions of Serval D are actually invoked as standard Unix command lines. So all of the tests are written in Bash. We've built ourselves a Bash test framework, and all of the functions are tested under the control of a whole bunch of test scripts that we have. And in this case, when we're doing that, instead of using TCP/IP to encapsulate all of our frames, we actually just throw all the frames into a file that just keeps growing, and we use the file as a way to simulate the network connection between a bunch of instances of these operating. So we're going to be able to, in future, run up tests where we have tens, hundreds, thousands, possibly even more instances of Serval daemon all running on a system using standard Unix files to communicate, and so we're going to be able to simulate meshes on the scales of cities, or this is part of the plan.
So small targets.
Yeah. We think only one city to start with. We want to make sure that the DNA protocol, as we evolve it, is actually scalable, so that one day, if you want to send an SMS to someone and all you've got is a Serval mesh covering your city, that it will actually find out the number and then find out the SID of the destination phone, and that you obviously won't be able to place a voice call because there'll be too many intermediate hops. But at least you can send a mesh MS. So it has to be able to resolve the SID and fabricate an MDP frame and start sending it. So we're going to start doing a lot of work to improve the scalability, or at least test the scalability of what we've built. And in the meantime, it's really nice to have a whole bunch of tests, because we don't know what percentage of our code is covered. I think it's probably about 60 or 70% of our C code is covered at the moment, but we haven't measured that. But the way we develop at the moment is that when we start developing a new part of this, what we do is we first of all write the test scripts. So we use a form of test-driven development, which is the only way to just keep developing at a fast pace without constantly slipping backwards in quality.
Sorry to break this up, I'm sure you have a lot of long, complex, detailed questions. Unfortunately, we have no time for that right now. So if you can catch up with Andrew, say thank you to Andrew for a start.